Hi, and welcome to a video where we're going to do some additional practice with derivatives, these specifically including our exponential functions and some chain rule. So you might have seen this derivative with respect to x of e to the u written in one of these two ways. The derivative with respect to x of e to the u du, so here we're putting that chain rule in there, is itself e to the u. And then here's that chain rule, times the derivative of u with respect to x, again, assuming u is some function of x. Or you might have seen it written, derivative with respect to x of e to the u is e to the u times u prime. Now we could have finished this with times natural log of e, and I'll show you where that comes from here in just a second. In the last one is just some basic exponential where our base is a. Our base is a constant, much like it is here with e. E is a value, 2.7 and change. It's a constant value, so our base is constant, and the exponent is where our variables are going to lie. So these are our exponential functions. When I take the derivative of a to the u, it is itself a to the u, then apply that chain rule, u prime. Then here's the piece that I was just talking about. I have to multiply by natural log of a. And again, if you've learned natural log derivatives already, you could take some function like y equals 2 to the x. You could take the natural log of both sides. My natural log property tells me I'm allowed to bring down that exponent. Natural log of 2 is some coefficient. So this is a coefficient of x, much like we would see in maybe a 5x, for example. So now that I'm ready to do this derivative of natural log of y is the derivative of that argument, or y prime, over itself, y. And the derivative of x times natural log of 2, well, again, natural log of 2 is a coefficient of x, so that derivative would just be natural log of 2. In order to solve for y prime, I multiply both sides by y, and the original y is the original function, 2 to the x. Now here I did not have necessarily a chain rule, meaning the derivative of x is 1. I don't have to say times 1, but I can sort of see where that natural log of 2 needs to come into play. So when you learned derivative with respect to x of e to the u, it is itself e to the u times that u prime, and technically there is that natural log of e, or natural log of the base, built in, but natural log of e is 1, so we don't need to write that down. Okay, so hopefully those derivatives are sort of in your memory bank already, and let's just apply them. Let's do a few examples here. So if I'm given the function f of x equals the quantity e to the 5x minus 9 all raised to the 7th. This overall is power rule because I'm taking all that stuff to the 7th. So I can start right away with my derivative, and I'll write the derivatives in the order that I'm doing them. So I'm going to do power rule first. I'm going to bring down my exponent. Going to keep my base the same. You never change a base or change an angle unless you use an identity. So again, power rule says bring your exponent down in front of your base. Keep your base the same. Subtract 1 from your exponent, so now that's a 6. And then I will chain rule, so times the derivative of what's inside. So the derivative of e to the 5x would be e to the 5x times that derivative of 5x, which is 5. I have an appropriate correct derivative right here. If you wanted to do a rewrite, because maybe I can see an opportunity to multiply, 7 times 5 is 35, and I'll just write that e to the 5x also in front of the quantity e to the 5x minus 9, all raised to the 6th. That just might be less typing. These are equivalent answers. So I did power rule followed by chain, and when I did chain, I needed the exponential function's derivative with chain again. Okay, let's take a look at number 2, and again I want you to kind of zoom out when you first look at these functions and see what's happening with my f of x. That will help you identify which rule you are supposed to be using. So if I look at this f of x, I overall see a product rule. And by overall seeing a product rule, that's what I'm going to apply first, and then for each derivative of each factor that I take, I might have to apply a different rule. I can see once I get to needing to apply the derivative of e to the negative x squared plus 9x, I'm going to certainly have to use the exponential derivative for e to the u, which will include chain rule, so times that du. So again, I will highlight these. Here's my function 1, here's my function 2, that's giving me product rule. So I will do the order in which I see them. So I will do the derivative of x to the 5th first, that is 5x to the 4th, and I'm going to leave this e to the negative x squared plus 9x alone. Now I'll leave that first factor alone, x to the 5th, and now I'll do the derivative of e to the negative x squared plus 9x, which is itself technically times natural log of the base, which is natural log of e. I don't need to write down 1. And then times the derivative of that exponent, negative 2x plus 9. And what you are going to notice with e's, this is a correct derivative, by the way. It could be done and move on. Now what you are going to notice with e's, because in the exponential, it's in the original function and in its derivative. Right now I see that I have two terms. Here's my first term and here's my second term. And when you see these two terms, you're going to notice that that exponential function e to the negative x squared plus 9x is in both. Again, because if that's your original function, it's in both your function and its derivative. So I will go ahead and factor out. I can also factor out x to the 4th. So maybe for e's later on, so I'll factor out the factor of x to the 4th and this e to the negative x squared plus 9x. And then what do I have left over? Well, from that blue first term, I will just have 5, right? Because the x to the 4th got factored out. And that whole e to the negative x squared plus 9x got factored out. Plus, and then from the green, I'll have 1x left over, and then times that quantity, negative 2x plus 9, because the e to the negative x squared plus 9x got factored out. And if I wanted to rewrite this again, I can distribute that x through. And so maybe I could say I have the quantity x to the 4th as my first factor, e to the negative x squared plus 9x is my second factor, and my last factor is negative 2x squared plus 9x plus 5. You don't have to write that in descending order if you don't like the negative term first. The benefit to this final one is later on in the course when you need to set this equal to 0 and solve for something, it's already in factored form and solvable. But certainly you have a correct derivative way up here, first step. Okay, one more. So let's take a look at exponentials when our base is not e. What if our base is a 3? All right, well, that's one piece of this. But overall, I see, and hopefully you see, quotient rule. And then within the quotient rule, when I need to do the derivative of that numerator, I then need the exponential with chain and overall power rule for technically the 17 and that denominator. All right, so here we go. So I'm going to say for this notation, the derivative of y is dy dx, or derivative of y with respect to x. Again, some people just write y prime, but I'd like to get you used to all notation here. So dy dx is, we're going to apply quotient rule. So it's low, I'll copy down 6x to the 4th. D high, so here's where I'm doing the derivative of the high. So the derivative of 3 to the 5x is itself times natural log of 3 times the derivative of that exponent. Derivative of 5x is 5. Derivative of plus 17 would be 0. So here's my low d high minus the high. I will write it down. D low, so the derivative of that denominator is power rule, 24x cubed, and it's all over low squared. You have a correct derivative here. Again, do I see an opportunity to maybe simplify this and make it look a little bit better? Absolutely. So I'll go one more step so you can get used to seeing that, or maybe 2 more steps. Let's see how long this takes us. So again, when you do quotient rule, you have 2 terms in this numerator. You have low d high minus high d low. So it is helpful if you can overall kind of separate that out or see that and make sure you know I have 2 terms. Can I factor something out of both of those terms? Sure, I can factor out a 6x cubed. Okay, so I'm looking really here. I cannot factor out 3 to the 5x because in my yellow that is being added to 17, so it's not an individual factor. So the only thing it looks like I can factor out of the numerator is 6x cubed. Okay, so then what I have left is an x, that 3, and I'm going to do this so we can really see it. I'm going to put that bracket there. So I have an x left from the blue. I have the 3 to the 5x, natural log of 3, and a factor of 5. And then in the next yellow term, I have that 3 to the 5x plus 17 as a factor. And if I take out 6x cubed from 24x cubed, I only get 4 as being left over. And then that's all over 36x. Now, x to the 4th quantity squared does make x to the 8th. Think about x to the 4th times x to the 4th. Okay, I can go one more step, not too tricky here. 6 divides into 36, leaves a 6 in my denominator, and x cubed will divide into x to the 8th, leaving x to the 5th. So if I wanted just maybe a little ease in typing this into a system, I also might write 5x as one factor. Otherwise, I'm just copying my numerator down. But my denominator became a little bit nicer, 6x to the 5th. Again, this should be equivalent to that. You should be able to graph it and see that the graphs do trace each other, because again, they should be equivalent. You were just rewriting it for ease, maybe in solving or manipulating it later. So I hope you found this video on some exponentials with some chain rules, some product and things like that helpful. Thanks for watching.